Have you ever looked up at the night sky and seen a tiny point of light moving steadily across the stars? That was a satellite, and it makes you wonder, right? What is actually keeping them up there? Well, today we're going to unpack the incredible physics that stops thousands of these machines from just falling out of the sky. I mean, just think about it. Right now, as you're listening to this, there are literally thousands of satellites circling our planet. It's this massive, invisible highway of technology whizzing right over our heads, and it forms a network we depend on pretty much every single day. So, that brings us to the big question. We all know gravity is a thing. It's constantly pulling everything down. So why don't these incredibly complex and, frankly, very expensive pieces of tech just come crashing back to Earth? It's a fantastic puzzle, and we are about to solve it together. Okay, so the first piece of this puzzle actually starts with a concept that we're all pretty familiar with, the idea of a constant fall. Let's uncover the first powerful force that's at play here. And that force is gravity. Of course it is. But here's the twist, and this might surprise you. Satellites are always falling. Every single moment, gravity is yanking them toward the center of the Earth. So the real mystery isn't why don't they fall? The real question is, how do they manage to keep falling without ever actually hitting the ground? So if they're always falling, there has to be something else going on, another force in the mix. And you'd be right. This is the secret ingredient that makes the whole thing possible. And here it is, forward motion. And we're not just talking fast, we're talking about mind-bendingly fast. To stay in what's called low Earth orbit, a satellite has to travel at about 17,500 miles per hour. That immense sideways speed is the absolute key to fighting back against gravity's constant pull. So, we've got our two key players, a constant pull downwards from gravity and a massive push sideways from forward motion. Now, let's see how these two forces, which seem like they should be fighting each other, actually combine to create something, well, something pretty magical. I like to think of it as the dance of orbit. You've got gravity constantly trying to pull the satellite straight down. But at the exact same time, you have this incredible forward momentum that's trying to fling it away in a straight line out into space. And guess what? Neither force wins. Instead, they work together, creating this perfect, continuous, stable, curved path. And that is an orbit. This quote is probably the best way to picture it. Satellites are in a state of perpetual free fall. But because they're moving sideways so incredibly fast, the Earth's surface is constantly curving away from them as they fall. They just keep missing. They're not falling to the planet, they're falling around it. And that right there gives us our perfect definition. An orbit is just that continuous curved path a satellite takes, created by that perfect, delicate balance between gravity pulling in and all that speed pushing it sideways. Now, this isn't just some cool physics concept. This principle has fundamentally changed everything about our world. So let's take a quick look at how this cosmic balancing act affects our lives, like every single day. Seriously, anytime you use GPS to get somewhere, or you check the weather forecast on your phone, you are relying on a satellite that is perfectly executing this orbital dance. Our entire global communication network, our TV signals, even incredible scientific missions to other planets, it all depends on this elegant physical balance. So if you take away just one single thing from this, let it be this. A satellite stays in space because of a perfect, beautiful balance between two constant forces, gravity pulling it in and its own forward motion trying to fly away. And that leaves us with one last really fascinating thought. This whole system we've built, from your phone signal to deep space exploration, it all relies on this perfect balance. So, what do you think happens when that perfect balance is even slightly disturbed? Now that is a question for another time.